Okay, so, Assalamualaikum. Good afternoon. How are you? Apa khabar semua? Okay, Alhamdulillah. So 19 of you already in. Let's get started. Okay. So today, inshallah, we're gonna continue on junction breakdown, and I've informed you just now that we're gonna use the new PDF file to help elaborate our lecture notes, because the notes on this part are just quite brief. So I'm going to do some elaboration based on the new PDF file and a bit of other drawing to help understand the notes, right? So we're going to do, so let's recap what we've learned so far. So last time we have discussed up to um, diode properties, right? So IV curve of the diode. So we know that you can see the whiteboard, right? Can you? Okay, good. So we have discussed up to the IV properties of a diode, right? IV, or you can also use JV if you like. JV is current density and I is the current. So it's used in both cases actually. So sometimes people plot IV, sometimes it's JV. So it's trying to deliver the same message, by the way. So yeah, it's fine. So we have learned that the IV curve of a typical PN junction is something like this, going down there. Right, oh sorry, and there's a bit of small negative value there up to that point, right? So on the right hand side is where we have our forward bias, and on the left hand side is where we have our reverse bias, right? So positive voltage on the on the on the right hand side and negative voltage on the left hand side. So we know that if we want to have a forward bias connection, see, remember, how do you have a forward bias connection? How do you connect the terminal on the PN side of the diode? How do we have it? Forward bias? Ingat lagi tak? So how do you put your, where do you put your positive terminal on PN junction for positive for forward bias? So positive to P type, right? Yeah, positive to P type and negative to N type, right? So positive to P type, so it's positive to P type and negative to N type, right? Positive to P type and negative on N type. Okay, that's forward bias. So if you want to do reverse bias, on the other hand, so it's just the reverse of just now, right? So it's positive on the N side and negative on the P side, right? So that's how you configure forward bias and reverse bias connections on your diode, right? PN junction is a diode. So we know that the shape of the curve is like that, and we can also note that this is somewhere on the forward bias side. You can have somewhere here usually. It's called V cut in voltage, right? So it's normally somewhere about 0.7 for silicon. 0.7 volt is called cut in voltage. That's the point where your current starts to flow across the diode, and then you start to get exponential increase of current with increase of voltage. So that's called a cut in voltage, right, for the forward bias region. We also learned that there is a small current flowing in the reverse bias, well, it's not supposed to flow because we have learned that diode is a rectifier. Diode is a rectifier. So if you draw a diode symbol like this, which side is the P side, which side is the N side? Can you recall? Maybe from your electronics. Which side is the P side, which side is the N side? No idea? So P side is on the left hand side, N side is on the right hand side, right? So this one only allows current to flow in one direction. So that's why diode is the rectifier, and it doesn't allow the current to flow into the opposite direction, right? This one cannot because it's a rectifier. So there's the meaning for this symbol, right? It blocks the current to flow. So it only flows into one direction, which is given by this curve on the right hand side. This curve on the right hand side, it can flow only in one direction, but it couldn't flow on the left hand side of the junction, on the left hand side of the curve, sorry, right? So reverse bias, we're not supposed to get any current to flow. However, if you look at the diode equation, J is equal to J naught exponential QV over KT minus 1. So if you increase the voltage into the negative region, so you will eventually have J equal to negative J naught. J or I, if you want to plot I, then is I equal to negative I naught, right? So what is this called? What is I naught called? Still can recall? What is this I naught from the previous lecture? What do you call this? I naught? Anyone? Anybody? Leakage current, right? I naught is leakage current. So that means even though the diode allows the current to flow to one direction only, but we also have a small amount of leakage current flowing through the opposite direction, right? So it's not supposed to allow the current to flow into this direction to the left. However, we do have a little amount of current due to some leakage at the junction. So therefore you have the I naught, right? So where do you think you get the leakage current from? Kenapa kita ada leakage current at the junction? What's the root cause of the leakage current at the junction? It's actually due to thermally generated carriers in the depletion region, right? Thermally generated carriers in the depletion region, which causes the leakage through the junction in the opposite direction, okay? So it's due to thermally generated current at the junction. So if you go on to the left, if you keep moving on to the left, increasing the voltage, so the current wouldn't just stay like that indefinitely. However, at some point, it will just break. So the junction will actually break. Okay. So if you extend the x-axis on the left hand side, at some point you will see that the current will start to increase exponentially as well. So this is what we're going to learn today, right? This is what we're going to learn today, and this is called breakdown voltage, right? VBR is breakdown voltage. BR is breakdown voltage. So the moment you hit this point, your current is going to increase exponentially as well in the negative direction. So this is already beyond the junction breakdown point, okay? So right now let's go back to our lecture notes. All right, okay. Right, can you see the nodes now? Can you see the nodes? Yep, all right, that's good. So in the last section, we determined the effects of applying reverse bias voltage across a PN junction. We know that when we apply the reverse bias voltage, the barrier height at the junction will increase, the electric field will increase, so there will not be any movement of charges across the junction because the barrier just get higher. So however, the reverse bias voltage may not increase without limit, so that means at some point the junction will break, right? The junction will break, and um, ideally you don't want the junction to let the current flow in both directions, right? So because it's a diode, so you want the diode to conduct into one direction only, but when it hits the breakdown point or the negative direction, the current will be conducted as well, right? The current will be conducted as well. So that means now your junction conducts in both directions. So this is where your reverse bias current will increase rapidly. So the point where you start to see the huge increase in the current in the reverse direction is called breakdown voltage. And there are commonly two physical mechanisms that can cause the junction breakdown in the reverse direction. So to look into that, let's go into the PDF file just now that I've just uploaded to eLearn. Oh, disconnected. All right. Can you hear me now? Okay. It was just for a short time, yeah. Okay. All right. Probably the line fluctuates. Most of the time it's okay, but sometimes I don't know, it drops. That's why I failed to upload all the files last week. It was okay, but then 70-80% it went bad and it failed. All right, so yeah, it was intermittent. Okay, so if you look at this PDF, so now you can see the PDF, right? Can you see? Okay, that's good. So you can see under section 2, junction breakdown. This note actually covers junction breakdown and heterojunction as well, but I'm not gonna go through heterojunction on this. I'm just gonna look at junction breakdown explanation for you to understand more, right? So so you can go through this section 2, junction breakdown. With increase in voltage here, will increase voltage. There is a particular value called junction breakdown. Breakdown voltage. Sorry, breakdown voltage. Sorry, I need to put your friend here. So there is a particular value called breakdown voltage beyond which the current increases rapidly. So we've seen that in the drawings now, where you can see an exponential increase in the reverse current through the diode with a high value of negative voltage, right? So there are two main mechanisms of junction breakdown, and the breakdown mechanism depends on the doping level, right? Depends on doping level. You can see it from here. So let's move on to the next page on this PDF. So you can see a schematic there. The first mechanism is called avalanche breakdown. And the second mechanism is called Zener breakdown. Pernah dengar avalanche breakdown? Have you heard of the word avalanche? No? In song, yes, in song, right? Pernah avalanche. So what does it mean? Literally, what does it mean? Apa maksud avalanche? Where is it? Hold on. I don't have with me now. Yeah, landslide, right? Landslide. You can see from you boleh tengok landslide snowfall kan? Snowfall dekat Kathmandu ke, kan? So if there is avalanche, then you can see a huge snowfall from the slope. Then Siapa yang ada kat situ memang tak sempat nak selamatkan diri. So it's avalanche. It's a lot of snowfall. So in this case, it's a lot of carriers. Salju runtuh, sama landslide, snowfall. Look at this figure. P-N junction. So you have depletion region in the middle. So you have electric field in the middle. So you have P on the left, N on the right, and the junction is connected in reverse bias, where negative terminal is connected to the P side, positive terminal is connected to the N side, right? So let's see the explanation below there. Avalanche breakdown in lightly doped key is lightly doped PN junction. So avalanche breakdown takes place in a lightly doped PN junction. So lightly doped means in this case it's as light as possible up to somewhere 1017, right? Up to 1017. The thermally generated carriers in the depletion region get accelerated by electric field, cause ionization in other silicon atoms, producing a cascade of electrons and rapidly increasing current. So what happens is when you increase the negative voltage significantly, right, to the high negative value, so what happens is that the electric field inside the depletion region will be a lot stronger. So a lot stronger, and then the depletion width will also be widened. So we've learned last time, if you change the forward bias or reverse bias, you will actually change the depletion width, right? And in the case of reverse bias, depletion width actually gets a lot wider due to the high negative voltage applied across the junction. So and it will also impose a huge electric field across the junction at the high negative voltage. So this high negative voltage results in accelerated electric field, or bigger electric field, actually bigger electric field that will eventually accelerate the carriers, which is electrons, for example, electron hole pairs in the in the depletion region. So when you have a lot of carriers, a lot of electrons, for example, accelerated in the depletion region, they will actually collide with the silicon atoms. Remember, dalam depletion region, we do still have silicon atoms, right? Betul. Kita ada silicon atom. We have ionized dopants, right? And ionized dopant, if you revisit the covalent bond of silicon to silicon to dopant, kita dah discuss hari tu. Every silicon atom is bonded to the neighboring 4 other silicons, right? So the moment you dope the silicon with, for example, phosphorus, the phosphorus will actually replace the silicon in the bond, and the phosphorus will be in the lattice, right? So silicon is still in the depletion region. So, and the valence electrons of the silicon are still there. So the free carriers at this point will be accelerated by a huge electric field in the wider depletion region. So they will actually collide with the valence electrons in the depletion region, causing ionization, right? So that means bila the free electron to accelerated, they akan knock another valence electron from the silicon atom in the depletion region, and satu electron they akan knock another electron. So you're going to have eventually 2 electrons. The first one is the free electron, the second one is the valence electron from the newly knocked atom, and then these 2 electrons will knock another 2, and then you're going to have 4, and then it will be avalanche effect. So that means 1 is going to knock, you're going to get 2, 2 you're going to get 4, 4 is going to get 8, 8, 16, all within a fraction of a second. So that means this is called impact ionization. Impact ionization, let me type. It's called impact ionization, right? Where your free electrons accelerate and knock down new valence electrons from the silicon atoms in the depletion region, causing more and more free carriers to be generated within a fraction of a second. So so these accelerated carriers, right, eventually produce cascaded reaction, cascaded production of electrons, generation of electrons, and thus generating a huge amount of electrons as free carriers. So the moment you have a huge amount of electrons as the free carriers, you get a rapidly increasing current in a negative voltage, in a negative region, right? So this is how you actually get the avalanche effect. So avalanche effect, so basically avalanche, let me type it down, originates from impact ionization. So avalanche effect originates from impact ionization that is produced by high negative voltage in the depletion region. Okay, so let's look at explanation here. So avalanche breakdown occurs in moderately and lightly doped p-n junction. So that means it's from as low as low dope 10 12 17 12 13 14 up to moderately dope, perhaps around 16 17. So you will have avalanche effect, right, with a wide depletion region, because we have a huge negative voltage across the junction that will cause the widening of the depletion region. So kita dah tengok schematic tadi kat atas. Electron hole pairs thermally generated in the depletion region are accelerated by external reverse bias. So originally kita dah ada thermally generated carriers, electron hole pairs in the depletion region. So they are accelerated by external reverse bias. So electrons are accelerated towards the N side and hole accelerated towards P side. So electron can interact with other silicon atom. This is just my explanations now. So if they have sufficient energy, they can knock off electrons from these silicon atoms yang ada dalam depletion region. So this will be a cascaded reaction, right? More and more reaction. Cascade, 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 one after the other. And this mechanism is called impact ionization, right? So this process is called impact ionization and leads to production of a large number of electrons, causes rapid rise in the current. So that means if you look at the current in the right, if you can see this, you can still see the whiteboard, right? Boleh ya, still nampak kan? Can you? Can you see the whiteboard? Can, right? Ah, cannot. All right, let me. Oh, you cancelled now. Alrighty. So yeah, okay now. Can see, right? Yeah, okay, can. So if you're talking about the impact ionizations now, so this is the region where you start to have impact ionization. So that means here at this point, sorry, this point onwards, I'll just so this point onwards is where you start to have, sorry, this point onwards is where you start to have impact ionization to the left, right? Where you see the high amount of high value of current in the reverse direction, right? So it's called impact ionization. All right, so let's go back to the PDF. This causes a rapid rise in current. The breakdown voltage decreases with increase in dopant concentration. So that means if you have a larger doping for your P side and N side compared to lower doping of P side and N side, so you're gonna have a lower breakdown voltage for the high doping junction, right? Katalah you punya junction, junction A has 10 18 10 17 on P side and N side, and junction B has 10 15 10 14 for both P and N sides. So that means you're gonna have lower breakdown voltage for the first junctions now, 18 and 17, because you already have more carriers at the junction to cause the cascaded effect, to cause the impact ionization. So you already have a lot of carriers to begin with. So that's why it's a lot easier for the junction to break in the case of heavy doping, right? So the large current during the breakdown can be modeled by a multiplication factor that relates the current to the breakdown voltage. So yeah, this can actually explain the amount of current, if you like. J is equal to M. M is the multiplication factor, right? Times J naught, Js naught, saturation current density, and M can be calculated like this using the reverse saturation current, Js naught, VR is the applied voltage, VBR is the breakdown voltage. This M is just for us to know how much current do you have, how much fold of current increase in comparison to the reverse saturation current, right? Right, you can also see this fact on the curve just now. I mentioned that if you have a higher doping concentration in the PN junction, you're going to end up with lower breakdown voltage, or VBR. So on this curve, you can see that if you move from the left to the right, lower concentration to higher concentration, so the breakdown voltage is reduces, right? It reduces. So that means you're going to need lower and lower breakdown voltage if you use a heavily doped junction. So yeah, look at the caption of figure 3. Avalanche breakdown voltage is a function of dopant concentration for different semiconductors. Yeah, different semiconductors certainly have different breakdown voltage versus impurity concentration characteristics. So but it's not so much different though. With higher concentration, the mechanism changes to Zener breakdown. So just now I told you that there are two mechanisms causing the junction to break. So if you're working with a junction with lower doping to moderately dope, we tend to have avalanche breakdown. We tend to have avalanche breakdown. And if you work with doping higher than 17, say mid 17 or 18 or 19 on both sides of your PN junction, so you tend to have Zener breakdown, right? So avalanche breakdown is for lightly doped and moderately doped, and Zener breakdown is for heavily doped junction. Right? Is it okay so far before we move on to the Zener breakdown? Okay, avalanche can follow, right? Okay, right. Okay then. So yeah, all right. With increase of doping concentration, so the breakdown mechanism changes from avalanche to Zener mechanism, or Zener breakdown. So what actually happens is that at this in this breakdown, we're gonna have tunneling effect, tunneling mechanism across the junction. I'll show you a little bit later. Why is it so? Even though we are applying high voltage, we know that applying high reverse voltage causing the depletion width to widen. However, if you have a higher dopant concentration on both sides of your junction, you will actually reduce the depletion width as well at the same time. So it depends on the magnitude of voltage on the reverse bias and the magnitude of doping level on both sides of PN junction, but effectively the depletion width will be reduced due to high dopant concentration on both sides. So also the reverse bias causes an offset in the bands such that it's possible for the carriers to tunnel across the narrow depletion region. So the depletion region now gets a lot narrower. So the tunneling mechanism here is from the valence electron in the valence band crossing to the conduction band in n-type. So sorry, the p-type valence electron in the p-type will actually tunnel into conduction band in the n-type. So I'll show you the schematic in the lecture note later. So this tunneling process is shown in figure 4, right? You can also see down here in figure 4. So you can see the valence electron on the p side, on the left hand side, if you look at figure 4, right? So the moment you stretch the reverse bias voltage, so the electrons in the p-type in the valence band can actually tunnel through tunnel through to the conduction band in n-type. So this can only happen at high doping level, right? At high doping level. In the low doping level just now, when you discuss about the avalanche effect, there's no tunneling mechanism because the doping level is low. So let's look a little bit at tunneling. This tunneling process is shown in figure 4 just now, where electrons tunnel from the valence band on the p side to the conduction band on the n side, driven by electrically externally applied reverse bias, the negative voltage that we're talking about, right? Besides, the tunneling also lead to a large increase in the current. So same thing. So the moment you have tunneling of carriers across the junction, you will have higher current in comparison to the saturation current density, leakage saturation current density. So the transition from avalanche to Zener breakdown will take place as the primary breakdown mechanism due to the high dopant concentration. Zener diode is used as surge protector in circuit where, since the rapid increase in the current, in current will happen with a small change in voltage. So I'll show you a curve down here. Yeah, all right. Okay, then you can see here, kalau you plot breakdown voltage on the y-axis in figure 5 against dopant concentration, you can see that if you're talking about 1014 to mid 17, that means avalanche breakdown will dominate, and if you're talking about heavily doped PN junction beyond mid 17, a tunneling mechanism or Zener breakdown will dominate. So, right, okay. Hold on, right. So let us go back to the lecture notes. No, it's shared already. Okay. Okay, so you can see the lecture notes, right? Okay. So so basically there are two physical mechanisms that are responsible for the junction breakdown in the negative reverse voltage region. So Zener and avalanche. Avalanche dominate at low doping to moderately doped, where the Zener breakdown dominates in the heavily doped region, right? So right, this is Zener breakdown. If you look at this, so Zener breakdown occurs in a highly doped PN junction through tunneling mechanism or tunneling process. So we've learned that just now. It takes place when the doping is beyond 17, right? Beyond 17, you can have Zener breakdown, right? In a highly doped junction, the conduction and valence band on the opposite side of the junction are sufficiently close. So when you stretch the voltage, so they will become a lot narrower because of the narrowing of the depletion region, right, due to the heavily doped junction. So such that the electrons from the valence band here, can actually cross to the conduction band down here. It's actually down here. So you can actually cross the conduction band in the n-type. Right? P-type is on the left hand side, n-type is on the right hand side. So electron can cross from the valence band of p-type into conduction band of n-type. So this is called tunneling process, tunnel through. So you can only have this effect in the heavily doped region. Okay. For avalanche, it occurs when the electrons or hole moving across the space charge region is now in the lower dope, in the lightly dope or moderately dope, right? You've seen from the curve just now, usually up to 1017. So anything below 1017, 17 has any 17 cm. So you have this effect in the reverse bias direction due to the sufficient energy acquired by the free carriers in the depletion region that can knock the valence electrons from the silicon atoms in the depletion region, right, causing cascading effect. So the newly created electrons and hole move in the opposite direction due to electric field, create reverse bias current, just like what you saw on the curves now. So this is the region, okay. So the newly generated electron hole pairs will actually collide with another silicon atom, with more silicon atom, so creating impact ionization and therefore the avalanche effect, right? So for most PN junction, the predominant breakdown mechanism will be avalanche effect, because if you talk about diode, there'll be some application that really need to go to high doping, but most of the applications typically use somewhere 1014 up to 1017 doping levels for the application, right? Right, this is just the illustration of the avalanche effects now, so you can actually draw this back as a normal PN junction. So this one is the depletion region in the center. So PN is on the left hand side, right hand side. So the central region is where you have the impact ionization, right? In the middle region, okay? So therefore you're going to have your reverse saturation current, reverse current to flow, okay. Let me share with you another one. Hold on, where is it? Couldn't see now. Hold on, yeah. Close already. Yep, no problem. Yes. Yes, I think that's all for today. It's a very short one. So we have learned that there are two common mechanisms that can cause a junction breakdown. Avalanche on the low side, low doping side, and Zener breakdown is on the high side. You can also find this if you look on the internet. You can also find this shape of the curve, IV curve. Let me show you something before we end. This is the typical shape of the IV curve, right, on the forward bias side. And in the reverse bias, right. So kalau you tengok the breakdown voltage in the reverse bias, which one do you think belongs to avalanche and which one belongs to Zener? Based on what we learned today, agak-agak which one is number 1 or number 2, avalanche or Zener breakdown? Right, let's guess. Anyone? Number 1. Okay, number 1, is it avalanche or Zener? Fazira cakap first avalanche. Alright. Faika, avalanche is 1. Right, Naim, avalanche all 1, right? Kenapa 1? Kenapa 1 avalanche? What's your reason? 2 breakdown voltage ni. So that means 2 is Zener, right? Kenapa the first one? High voltage. High negative V. High negative V cause avalanche, right? Yes, correct. So the answer is correct. So maksudnya you faham lah. So maknanya reverse, if you reverse too high, so if you reverse it low voltage, you will easily get you'll easily get Zener diode provided your PN junction is heavily doped, right? So if you need a higher breakdown voltage, that's a sign that your junction is not heavily doped, right? So just now we have also seen that if you plot VBR over doping concentration, you can also see this shape, right? So if you go to higher doping level, so you need a lower breakdown voltage. Negative lah, negative, tapi lower breakdown voltage. So that means you will have avalanche here, and you have Zener here, right? First region here is all for avalanche, and the second region is for Zener diode, right? So this one low doping, this one high doping. All right, avalanche, Zener. All right, okay, yeah, that's all for today. Any questions? Habis awal lah. No questions? Semua okay? All good? I'll try to upload again the files. Saya dah try, I think near 10 times. Kadang-kadang fail. Kadang-kadang fail awal, kadang-kadang fail dekat ujung-ujung. Fail ujung tu yang sakit hati ya. Wah, dia nak okay lah, suddenly 90% gone, fail. I'll try again. Yeah, so we're done with PN junction under bias. So Naim boleh tak explain sikit pasal okay, ada internet problem okay, avalanche, right? Avalanche breakdown will happen at a high negative voltage. If you compare with Zener, so you will need higher negative voltage for you to get avalanche breakdown. Sebab in the first place, because your PN junction is dope lightly to moderately. So that means kalau you punya PN junction is about 10, dope 10 to low doping lah, 10, 12, 10, 13, 14, up to around 17, you will have avalanche breakdown. So if you go for beyond 17 or higher than mid 17, you'll tend to have Zener breakdown, right? So why do we have avalanche breakdown? Kenapa kita ada avalanche breakdown? Because when you supply high negative voltage, so the thermally generated carriers, the free carriers in your depletion region will be energized. Dia macam ada, bila you bagi negative voltage, dia akan energize the free carriers in the depletion region. So the high electric field that you supply during the negative voltage will cause acceleration of the carriers, dan carriers ni dia akan collide with the valence electrons from the silicon in the depletion region. So because in the depletion region we still have the silicon, walaupun kita dope dia, tapi if you recall back when we talk about doping last time, you need to have either dopant in the lattice, either p-type or n-type in the silicon lattice. So that means when the silicon, each silicon is bonded to another 4 neighboring atoms, so phosphorus or boron akan replace one of those atoms to be able to cause conduction, right? So that means valence electrons are still there in the valence bond, in the connection there. So therefore accelerated carrier study, dia akan collide dengan valence electrons, will cause more and more electrons to be free. So valence electrons dia akan knock off and will become free, and you eventually get more and more electrons, and these more and more electrons will also be accelerated by the high electric field due to the negative voltage bias. So they'll cause more and more reactions. So these more and more reactions is called impact ionization, right? Impact ionization. Let me put it down again. Impact ionization, cascaded collision. So it's called impact ionization. So impact ionization ni dia akan menyebabkan elektron tu langgar, and you eventually have avalanche effect. So you eventually have avalanche effect. Macam snowfall on the slope of Everest ke apa kan. So you have avalanche effect. So that means you're going to have tremendously high amount of electrons at the junction, and this will give rise to reverse current at the high voltage. So that's why you have the high exponential increase at the breakdown voltage. Okay, Naim? You get now? All right, that's good. So on the other hand, if we talk about Zener, so that means when you have your diode heavily doped on both sides, so you will have tunneling effect of valence band electrons from the p-type into the conduction band into n-type, or of n-type, of n-type. So this is called tunneling process. Okay, nanti kita akan belajar this in the semiconductor devices. So why do you think it's important, before we finish, why do you think it's important to know the breakdown voltage? Why do you have to know, why do you have to bother about breakdown voltage? Any ideas? Any guess? No idea? Right. If you want to operate a normal diode, you want to know where's the operating region, right? You want to know where's the operating region. Nanti bila you buat presentation on the diode or whatever devices that have a PN junction, so you will probably see this as well. So you want to know the normal operating region of your devices, so therefore you don't want to exceed certain limit, right? You don't want to exceed certain limit that could cause breakdown to your junction, because some breakdown mechanism is reversible. Maksudnya kalau you, for example, assuming your negative voltage negative breakdown voltage is say 20 volt, negative 20 volt for example, that means kalau you bias more than negative 20 volt, you're gonna have breakdown of the junction. But if you reduce the negative bias back to perhaps around 10 15 10 10 minus volt, negative 10 volt, sorry, you'll probably recover the junction from breakdown. So that means the effect is a reversible effect. You will reversekan kesan tu. However, if you let the breakdown to happen too long and the breakdown voltage is probably too big, you probably end up with irreversible breakdown. So that means bila you dapat breakdown tu, you hit the voltage, for example, you hit beyond minus 30 volt or 40 volt for quite some time, you'll probably end up damaging the junction, right? You'll probably end up damaging the junction, and that is irreversible. Maknanya you punya junction tu dah rosak lah. You tak boleh go back to the other region already, because it's gone already, it's broken. So why do you think causes the reversible breakdown? Kenapa kalau kita reversekan dia high voltage, lama sangat dia akan experience irreversible breakdown? Maknanya completely broken. Any idea? Last question before we finish. Any guess? Agak-agak kenapa? Kalau what's going to happen from your electronics punya knowledge, kalau you dapat reverse current too high at high negative voltage, what could happen? You remember this equation? I type it down. Apa tu? Equation apa tu? P is equal to IV, right? So what is P there? Power. Yes, power. So apa jadi? When you have high reverse current, very high current, exponentially high current, high voltage, so you can end up with high power, right? Power. So how do you feel the power in the device? Macam mana you nak rasa device tu how do you translate that high P? Kalau you ada high I, high V, therefore IV is high, so your P is high. Can you feel the P? Can you feel the power? Yes, Hazika, great. High temperature, you can feel the heat, right? So the power is translated into heat. So that means you can feel high temperature. So that means the device is going to experience high heat dissipation across the device. So maksudnya kalau the power is just too high, your CPU is too hot, for example, or if your chip is too hot, your diode is too hot, and beyond the manageable limit by the device, then it gets broken and that's it. It probably melts. It probably melts at a very high temperature. So maksudnya kalau you design you punya diode tu, you have to know the thermal management side of it. So some of you ada buat FYP dengan Dr. Shan kan, right? So ada kan, you buat, ada yang buat heat management or heat dissipation device or something? Anyone, right? Ada kan yang buat dengan Dr. Shan kan? So I'm not sure whether you are working on the area or not, but if you do work with Dr. Shan, kalau you buat kerja dalam thermal management research lab, thermal lab dekat fizik tu kan, so you'll probably do some projects on heat dissipation or thermal management. So these are the things. So when you design your material for heat dissipation process, so you need to know how much heat can you handle, how much power can you handle. So therefore, to be able to know this, if you're talking about diode, so it's the breakdown voltage and therefore breakdown current and breakdown voltage and breakdown power, and yeah, all this heat management stuff, right? So your diode may end up melted due to the breakdown mechanism. So therefore, in this condition, it now becomes irreversible already. So you tak boleh reverse balik dia punya operation. So it's just gone broken, right? That's it. Okay, any other question on this topic? So we're done with PN junction under bias condition. So this Wednesday we're gonna start discussing about PN junction under illumination, right? So we want to trigger new carriers with illumination, right, using light. So the previous topic we've discussed about creation of excess carriers using bias voltage, right, and electric field and so on. So next one will be about light. Okay, tak ada soalan all good so far? Tak ada. So yeah, that's it for today. Thank you very much. So stay safe. Bye bye. Assalamualaikum.